Morning, everyone. How are you guys going? Hope you have had a good rest yesterday. And today we're doing something new for our D2 panel meeting, in that there will be NGN, Next Generation Group, joining us today via the webinar, WebEx. And it's an initiative driven from the Paris Central office that in that the involvement of the Next Generation Group will be more towards the different panels and for SIGRE in general. And hello NGN, if you can hear me, I'm Victor Tan, the convener of D2 Australian panel. Welcome. And today there will be a presentation that will be broadcasted via webinar, one of the presentations. And we're hopeful that in subsequent years this arrangement will continue, and with a few more presentations. Because this is the first time we're running it, so if there are any audio or video or technical issues over at the other end, just bear with us, because we're trialing it out for the first time. And at the end of this session, there will be a Q&A, as usual, for the regular panel members that are here today, and also for the NGN webinar members who would like to ask questions. You can type in the chat box, and Ken Wong and Kieran Rumligan, who are the D2 NGN representatives, they'll be able to relay your questions to the presenter. So without much further ado, I'll hand the time over to our presenter, Nick Lee from TC Comms, who will be presenting on teleprotection over IP.
Thank you, Victor. Good morning, everyone. I am Nick Lee with TC Communications, and we'll be presenting a topic that a lot of people have a lot of doubts that can be done, teleprotection over IP. But we've done it, and we had done it since 2008, so it's proven to work. So let's get going. Okay. A little bit about ourselves. We are TC Communications from United States, Irvine, California, to be exact. And we've been providing communication equipment, manufacturing, design in one location for almost 25 years. Yeah. And you can see there, our emphasis has always been on critical communication solutions. So very hardened products and products that are durable. Talking about 300,000 hours or better on the MTBF. You can see a couple of the standards we comply with: 16313, IEEE 16313, and also 61850-3 compliance. Ruggedized stuff, right? Industrial grade. And on the right-hand side, pre-sale and post-sale support is very important. So we're selling solutions, not products. Okay, some backgrounds in teleprotection, right? First off, and then we go into what we call multi-service Ethernet platform, MSEP, and some applications to talk about, three of them. And what are the challenges that we face when we push teleprotection over IP, and how we overcome those challenges. And a couple lab testing that we did for running mirror bits over IP, and also line differential E7L over IP. Right? And we need some time for the Q&A session. Okay, so quick background on teleprotection. So relays talk to each other in the past, whether through fiber or copper. Right, direct connection. And then fiber came along. We have relays that run on R232. You can just get a modem, right? Push that serial over fiber. That works point to point. Multiplexers came along, TDM, MUXes, right? So you got relays, R232 connection there, sharing with T1, Ethernet, telephones. Take advantage of the fiber that you have, right? Push multiple services over the paired fiber. Then Ethernet came around about, I don't know, 10 years ago, and starting to become the transport technology of choice for a lot of utilities. So what do you have in replacing the T1 muxes or TDM muxes? We have what we call MSEP, multi-service Ethernet platforms. So there's the same thing as a TDM mux, except that it's TDM over IP now, right? So you can see all these services that it supports right there. Okay. So why Ethernet? Well, Ethernet, it's a technology that you can share the bandwidth among other services. As we know, bandwidth efficiency is important. You're not locked down to a circuit that you carve out on the SDH or SONET network. Flexibility in network topologies, right? So you can set up rings or point-to-point, point-to-multi-point type of setup. And it's really easy to use, right? I mean, it's something that high school kid can log in and be able to configure a switch or have you. It doesn't take much expertise. And best of all, it's low cost, right? It's the latest technology, so equipment tends to be low cost than older generation of TDM, SDH equipment. All right. We'll talk about a few cases here. First one is a power utility that we work with in Paraguay. And their network is fiber and microwave systems, combination of both. And they're pushing R232 teleprotection interface and also C3794. The second one is an MPLS network in place with a company in Canada. And they run G.73 64K co-directional interface on that. They're using some Siemens relays there. And the third one is a utility here in Australia that has existing MPLS network on fiber, and so they use our solution for the C3794 conversion to IP. First one up, so it is in Paraguay. You can see there, it's one of many networks that we put in place, but you can see the MSEP connecting all the services, telephone and E1s and so on, but the protection relays from a company in Spain called Engine Team, and they were able to use their serial card on the MSEP there. MPLS, this Alcatel-Lucent stuff, and they have, during that time, a G.704 interface on their boxes, and we're able to take that over IP. And here in Australia, relays at each location, I believe these are SCLs and Schneider Electric, and again, IPML, MPLS network in the middle. Pretty straightforward. So what are the challenges we face, right? With Ethernet, you get packet losses. That's common if your network is not designed well enough. So you're going to face collisions and congestions and all that stuff, cabling issues, interference. And then there's also jitter, what we call packet delay variation on Ethernet, because Ethernet is a store and forward type of technology. So packets and going through the network, you're going to face jitters. Not that you don't face in the TDM network, but it's the same on Ethernet. Misorder packets. So packets arrive in from different areas of the network, right? Different paths. So you have to have a way to somehow rearrange that at the end. So that's something that also causes issues for Ethernet network. And a big issue that people always talk about or have questions on is how do you synchronize the signal coming from one direction to the other, which is what we call clock synchronization. Because as you know, Ethernet is a connectionless technology, right? So how do you still recover the clock that's, say, an E1 signal coming in at 2.048 and then recover at the other end? So to overcome the challenges of packet loss and delay variation, you can't set up a best effort Ethernet network. It has to be something that hardened, your equipment has to be hardened, full duplex, prefer fiber-based, but not very good solid connection on microwave or wireless connections and so on. You talk about RSTP, that's the ring protection convergence technology, and also ERPS is another one. So solid Ethernet connection is very important. And your misordered packets, you have to be able to interpolate, say, a packet that comes in, and then for synchronization purpose, you have to be able to inject another packet in place of it to maintain the clock, so throughout the transmission. And then we arrange the packets I mentioned at the end. And to make sure that you have a good path, you usually set up a what we call a pseudo wire connection. So when you nail the connection from one end to the other, the packets will always go through that particular path, unless the network converges and then it goes another, the RSTP or ERPS kicks in. So, but as long as you set up that good pseudo wire connection, there's always packets flow through that path. So, all right. Then on clock recovery, what we did was we use a method called adaptive clock recovery. So at the very end of the node, or from A to B, at the B side is where we have the technology to recover the same rate that's coming in from the other end, from A side. So it's fully compliant to ITU standards. You can see it there, G.823 and 24. So those are the very important aspects of overcoming the clock synchronization issue. So let's look at that a little bit further. So on a network, or we use what we call a water bucket analogy to show different networks. So on this one, you can see on the left-hand side, you have a water pump that's pumping around 10 gallons per minute, right? And then it's a pipe that's flowing through the B side. And if I have on the right-hand side a meter measuring the flow that's coming out, that's about 10 gallons per minute as well, right? But what if the pipe is broken and you take the pipe out and there's no direct connection? Then instead of feeding through all the way through, you have buckets of water that's going through and into a water tank, right? And from there, then you have another pump pumping the water out of the tank and then out to the another bucket or reservoir there. So you have to have a way to regulate the B pump here. So we have our guy Pal that's doing the controlling of the rate. Okay. So water is flowing and he's operating the pump, and the rate is at the moment 11 gallons per minute because the tank is full, so he has to increase the rate so to keep the water level in the middle of the water tank, right? Now the water drops and to a lower level, so he has to decrease the flow to increase the water tank level. Right? So it's doing all that work, right, to somehow get the pump to regulate at 10 gallons per minute. The flow to be even so that the water tank level stays consistently in the middle. Now, the water buckets are going in at a consistent rate, but there are some buckets that are smaller and bigger and so on. And so the water tank level is going to go up and down, and he's sweating. He's controlling the thing, and a lot of hard work. Yeah. So what we're doing here, basically, you can see it's emulating a TDM traffic over IP Ethernet packets, right? You have all these individual packets coming in, and variations of packets, variations of delay. And to replace our buddy PAL, we have a digital phase lock loop that's tied to the jitter buffer, which is represented by the water tank. And with that, we're able to provide a consistent clock in and at the rate that's the same as what's coming in and going out of the network. I'm doing this in a very slow environment, slow process, but in reality, it's pretty instantaneous. Whatever comes in, whether it's 64K or T1 rate or E1 rate, it's very fast. Yeah. So a couple of lab results to show you guys. And first one is to determine SCL runs a protocol called bits on their relays. So just want to see how it reacts with the MSEP converting TDM to IP. So we set it up in the lab. You can see there we have the GPS connected to both sides, with the equipment, TDM over IP equipment in the middle, and just to see what the delay numbers will be on the, we're triggering all that to the relay 125 volt DC inserted and applying the triggers. So here's a screenshot of one of the tests that we did. And you can see this is back in 2013. And this one is at 120 milliseconds here. And the next one shows 129, so roughly around 9 milliseconds difference there. So you can see all the points. We did an average. Each test actually is roughly around 5 and 12 points. And these are the numbers that we come up with. So with direct connection, it's roughly around 9 milliseconds, point to point, inclusive of the relays. Then with over Ethernet, it's roughly around 1 point, almost 2 milliseconds of delay. So not much. On the second test that we did, okay, so this is running 87L line differential protection scheme over C3794 over fiber. So same type of setup. You have GPS connections to a couple of SCR relays there and over 80 kilometers of fiber. Again, TDM over IP type of setup. And we use the Omicron to set the test patterns to the relays. So what we see is on the network side, you get roughly between the two C3794 cards, it's around consistently about 1.6 milliseconds. And the overall delay ranges anywhere from 15 to 21 milliseconds. And here's the results of that. So you can see On the left-hand side, you have the network delays. I'm missing my pointer. Okay, let's try that here. So relays run a method called ping pong. You send a signal, you get something back, and you average out the delay. So it's somewhat accurate. Not as accurate as when you hook up the GPS to the relays and actually you have time stamped and all that stuff. So with the connection, this is with 3 meters of fiber between the relays. Network is roughly around 1.6, and this is the overall delay inclusive of the relays. Yeah. And here's the phase angle measurement. With 87L, it's constantly measuring the phase angles of the currents, and so that's the number that we see in the lab. And when we introduce 80 kilometers of fiber in the middle, you can see the network delay is a little bit longer, but yeah, everything else is pretty much the same, but the angle increased, so the accuracy is not there. With GPS connection, 80 kilometers, pretty consistent, a little bit higher on the delay, but if you can see here, the angle measured is 0. So that means whatever the angle that's coming in and going out, the difference in that is very close to pretty much identical, right? With the unit, the bandwidth on the TMOIP device, on the IP side, it's gigabit. So we introduce or inject 500 megabits of bandwidth into it, just to see what the reaction is. So half of the bandwidth is utilized, and the other half is for protection. So not much difference. The same goes for 800 and also gigabit. So injecting external traffic to the Ethernet pipe at 100%, and you're still getting the results that you want. That's because you're able to set up priority for the teleprotection link. So queuing and all that stuff, primarily, or the primary connection is dedicated for the teleprotection. Everything else is secondary, right? So yeah, looks great. Okay, just some photos to show you guys. Setup we have in the lab. Relays, products, GPSs, triggers on the back of the relays there. So in summary, you know, we overcome the challenges of packet losses, PDVs, and the misorder of these packets, and so on. And most importantly, the clock recovery on the other side. So, and we feel that it's good enough for teleprotection over IP. That you know, Ethernet is a good platform. It's like I mentioned, we've done this for 8 years now, so we have multiple cases, and so we can discuss all that offline if we need to. This is a quick video to show you guys. So how much time I have? Yes, right. So a quick introduction to the video. So a consulting company did this video at a trade show, utility trade show. And he was talking about the network that he put together for a customer in Texas. And he has many of links for differential relay protection over layer 2, layer 3, and even public MPLS network. So very successful, and 5 minutes video. Oh, sorry.
So the initial big concern was performance based on latency. The other concern is obviously reliability over the long term. My initial concerns were around performance. You know, being a classical protection engineer, I was really worried about how the IP backbone would perform in such demanding applications. And so the thing that really allayed those concerns for me was testing. The testing that we did was based on database that the customer, Texas New Mexico Power, had of relay misoperation data. And what we did was to set up a mock teleprotection over IP system and then play using satellite sync test sets every fault that had caused a misoperation on the system over the past several years, therefore assuring ourselves that the system would perform correctly. So the latency concern was addressed by a pilot project. Over the course of 6 months, we deployed a pilot system, and we're able to deploy it both in a lab environment using basic network attacks, flood attacks, and also in the field exposed to the other network traffic in the network with no QoS and no prioritization, and it performed perfectly. And then the reliability concern was addressed over time. To date, the solution has over 70 service years with no failures. So the original install went in early 2012, and it's been running since. And obviously, additional deployments have happened over time to bring the total install base to about 80 units. That has gained us about 70 in-service years with no failures. And this is in the Texas Gulf Coast environment where temperatures easily reach 100 degrees. We've actually had units in service at 60 degrees C ambient. You know, it's always a progressive thing, but certainly I'm more confident in the solution today than I was when I originally went in, to the point that I would strongly recommend it today over a TDM-based solution.
So that concludes the presentation. Any questions you guys may have, we'll address those.